Hello, I would like to welcome you to the last video of the Module 4, which is about the Lighthouse project at INDORE. My name is Roberta Graf and I'm a researcher at the Life Cycle Engineering Department of Fraunhofer Institute of Building Physics, IBP. After the previous submodules, I would like to address another topic with this video that is very general valid and gives a glimpse into the future. As you know, the buildings in INDORE have been constructed or are being constructed using sandwich construction. These sandwich wall panels are made of expanded polystyrene. As with the other lighthouse projects, the aim was to test a construction method that is both cost-effective and very fast. In addition, the methods used have good structural properties and are considered durable and long-lasting. However, most building materials, including those used here in the lighthouse projects, cause a lot of CO2 emissions during their production. Therefore, in this module I would like to give you the basics about what the global warming potential actually is and what it can be used for example for life cycle analysis. We will also look at a small example of how life cycle analysis works and how to calculate it, and especially on how to interpret it. Moreover, we will have a look at what computer software can be used for the calculation. In the end, I will then show you some examples in an interview of how the global warmings of buildings materials differ and how these are determined and measured and how material could be replaced in the future because they have better global warming potentials. But let's start from the beginning. What is the global warming potential actually? As you know, we are in a time where mankind has caused and continues to cause man-made climate change. Climate change is mainly driven by the increase of greenhouse gases in our atmosphere, as these gases are particularly good at absorbing the radiation that is reflected back into space. They thus form a protective layer between the Earth and space. This is of course important for life on Earth, but the increase in gases also raises the temperature on Earth, which we call climate change. But which gases can absorb how much energy and how well? In order to make this comparable, a reference gas was agreed upon as early as 1996, the well-known CO2. It thus has the greenhouse gas potential of 1. The greenhouse gas potential is made up of the following factors: the ability to absorb infrared radiation, radiation absorption spectrum, and lifetime in the atmosphere. All other greenhouse gases or greenhouse gas emissions are given in relation to this reference gas, thus describing their own greenhouse gas potential. Here you can see a list of different gases with different greenhouse gas potentials. Besides CO2, the best known are methane and nitrogen oxygen. Now, of course, several questions arise. Firstly, why is this of particular importance for the construction industry? This can be answered quite well when one sees the impressive values that 40 to 50% of the worldwide consumption of raw materials and approximately 37% of the emissions are connected with the construction sector. But where do these greenhouse gases originate? How do I quantify the amount of greenhouse gases? And what use is the value to me in the end? This is exactly why we look at the so-called life cycle analysis in the next step. Materials surround us everywhere and at all times, but the various building materials are of particular relevance to us. When a building project is usually planned, attention is often paid to the fact that the material fulfills its purpose and appears to make economic sense. However, due to the already mentioned relevance of climate change, another factor becomes important that reflects the ecological quality of a building material, or rather of an entire building. And in order to differentiate and evaluate this, the life cycle assessment comes into play. To put it simply, a balance sheet is about the question: what and how much do I have to put into a system in order to generate the output? From this, a definition of life cycle assessment can be given. LCA is the compilation and assessment of the input and output flows and the potential environmental impacts of a product system during its life cycle. This sounds rather complicated at first, but in principle it is easy to understand. The LCA looks at the 4 phases of a product: production, use phase, end of life, and recycling. Using the example of a building, we look at which products are used in which quantities in order to be able to add up the resulting greenhouse gas emissions at the end and thus have an overall life cycle assessment. At the beginning, the raw materials have to be extracted and built in an energy-intensive way. Then, the building is used for several decades and also consumes energy in its use, which causes emissions, for example. And finally, the building has to be demolished in an energy-intensive process, or materials may have to be recycled. Up to now, energy-efficient construction has mainly looked at the emissions that occur during operation, which is why the LCA now also takes into account the important aspects of primary energy demand in construction. Through this analysis, classical research questions can be answered, such as: which resource or emission can be saved if material A is used instead of material B? Or what alternative materials are available while ensuring the technical and functional properties of the product? This only works because life cycle assessment is a standardized and quantitative calculation of the total greenhouse gas emissions of a product, which ensures comparability. But life cycle assessments are not only interesting for research. Already now, and even more so in the future, competitive advantages will arise if ecological aspects are already taken into account in the planning stage, from which, in the best case, even an image gain will develop. And of course, there's also the aspect of contributing to global environmental relief. To make the theory about global warming potential and LCA more understandable, I would like to show you an example of how such a life cycle assessment is drawn up and what can be achieved through substitution potentials. The first step is to define our product system and keep everything transparent. Somewhere I have to set a so-called system boundary. Which process modules are part of the product system and which are not? For example, should the energy used to produce a machine that is needed for the process be included? Or is it sufficient to look only at the energy consumption of the machine in use? A further determination is the issue of allocation. In other words, what energy and material consumption is attributed to the end of the product. An illustrative example: in the extraction of diamonds, a huge amount of stone has to be mined and broken up. This process is very energy intensive, but the leftover stones, rubble, can be used well as a filling base for road construction. It must therefore be clarified how much of the energy used is ultimately allocated to diamond extraction. In an LCA for building, these values must therefore be determined for each material. To simplify an LCA, these data are often prepared and published in datasets. These data are, for example, published by product manufacturers themselves or by scientific institutes, all according to certain standards. In an LCA, these primary data or raw materials can then be accessed and therefore, for example, global warming potential can be read out. If no data is available, however, estimates must be made. In a global warming calculation, the data of the building material are collected in order to simulate the construction of walls, ceilings, and others. The individual data are then entered and converted to the functional unit to ensure correct comparability. We have an example house with a floor area of 10 times 10 meters and we want to calculate the global warming potential of the walls. You can see the wall construction here with a thickness of 0.2 meter. The data for the global warming potentials of the individual layers were collected in a database and entered into the respective life cycle phases A1 to C4, which corresponds exactly to the production phase, the use phase, and the end-of-life phases. These global warming potentials have already been converted to a functional unit, cubic meter, which represents the material reference quantity. However, since we want to know the exact consumption for the wall, the value is multiplied by the proportional volume of the building component layer. If we now add up all the CO2 consumed, the result is a total global warming potential. This means that 1 square meter wall element has a global warming potential of 26.49 kilogram CO2 equivalent. Our example house has 240 square meter, which means that the entire wall area causes a global warming potential of 6,357.19 kilogram CO2 equivalent. The great thing now is that a building material and thus the individual CO2 consumption can be changed to see how the global warming potential balance improves. In the future, material recycling will also play an increasingly important role, which could potentially lead to a reduction in the global warming potential consumption of the product in the life cycle assessment. For example, there would then be no emissions that occur in the extraction of raw materials, so that the recycled material could have an improved life cycle assessment. As I said, it will be far too time-consuming for you, but also for anyone involved in LCA, to determine every single global warming potential of a material, which is why you will inevitably have to rely on databases. However, since these each require a certain standard of data collection, this is accepted as a basis. Exactly which databases are suitable for you depends very much on the regions of the world, as there are differences in the types of production. Therefore, here you can see a few exemplary names of databases, mostly related to Europe, which can be used to feed the life cycle assessment. In addition, the way example calculation from just now is of course much too time consuming, especially when the scale of the project becomes much larger, so that software can be used to help you out as well. Typical LCA tools used you can see here as well. As we have previously discussed, global warming potentials are an important tool in understanding and mitigating climate change. These values, which measure the relative warming effect of different greenhouse gases, are used in life cycle assessment to evaluate the environmental impact of products and processes. But how exactly are global warming potentials measured for different materials, and how are the values in databases ultimately determined? The greenhouse gas emissions on a process level are determined through a variety of methods, including direct measurements, calculations based on known emission factors, and activity data, and assumptions based on engineering estimates or industry benchmarks. These methods may make use of physical and chemical models to estimate emissions, such as using chemical reactions to predict emissions from industrial processes or modeling the emissions from transportation based on fuel consumption and vehicle type. The specific method used will depend on the available data and the accuracy required for the analysis. It is important to use the most accurate and reliable method available to ensure that the greenhouse gas emissions are accurately estimated. The modular principle of the datasets allows us to take this process level information and use it to create other datasets. For example, we can consider the emissions associated with electricity production in the LCA datasets of materials with energy demand. It is important to accurately determine global warming potential and consider greenhouse gas emissions in LCA, as this helps us make informed decisions about sustainability. To answer that question, we need to consider where exactly the global warming potential of a building material occurs. Is it during the production phase, the transportation phase, or the use phase? Understanding the full life cycle of a material is crucial for accurately assessing its global warming potential and identifying opportunities for improvement. One way to reduce the global warming potential of a building material is to focus on reducing the energy required for its production. This can be achieved through a variety of means, such as using more efficient production processes or sourcing energy from renewable sources. Another option is to consider alternative building materials that have a lower global warming potential. For example, biogenic materials such as wood or clay have a much lower global warming potential compared to materials like cement, which has a high chemical CO2 emission during production. Lightweight construction is another important consideration. By using lighter materials and more resource-efficient construction methods, we can significantly reduce the environmental impact of a complete building. Finally, the type of construction itself can also impact the global warming potential of a building. Prefabrication, for example, can be more energy efficient compared to in situ construction. The last method to reduce the global warming potential of a material would be the so-called carbon capture process in production, which is a promising avenue for the industry. We will discuss that in the next module in more depth. It is clear that the way we currently build cannot continue as before if we want to effectively address climate change. But climate-damaging building materials currently have a cost advantage, which makes it difficult for more sustainable options to compete. So what can we do to make climate-friendly materials more competitive? One solution is through political decisions, such as implementing the so-called CO2 certificate trading. These systems put a price on carbon emissions and create an economic incentive for companies to reduce their carbon footprint. This approach is about assessing and evaluating building products in a different way. Instead of just considering the primary cost of a material, we can now also factor in its environmental impact and long-term sustainability. It's worth noting that this new way of evaluating building products is not yet widespread, but more and more countries are introducing these types of systems. So it will inevitably affect the global building material market. And with that, I would like to thank you for watching this video. See you in the next module about the Lighthouse projects.